Hello, everyone. Thank you for joining us today. Welcome to another session of Steam Management's webinar series. Today's session dives into how blowdown heat recovery systems work to improve boiler plant efficiency. You'll learn what it is, when it works, and how to calculate savings. Leading today's discussion is Chase Bean, Steam Management's Vice President of Revenue and Engineering. Chase leads the SMI engineering team and has over 18 years of experience in the energy sector, spanning engineering, project management, and business development. Following the webinar, you can email Chase at that email for a PDH certificate, and his email will also be shown at the end of the presentation. You're welcome to ask questions in the chat at any time. We'll address them during the presentation, and we'll also leave time at the end for a Q&A. This session is also being recorded, so if you need to step away, the recording will be shared after the webinar. Thanks again for tuning in. Now I'll hand it over to Chase to get started with the presentation.
Hello, good morning, everyone. We are Steam Management, and we provide turnkey retrofit projects with a focus on efficiency improvement in steam systems. These solutions reduce system energy costs, conserve water, and reduce carbon footprint. We work in a variety of markets, basically anywhere that has a decent-sized steam system. We have something to offer. Our disclaimer here. The presentation is intended for technical and educational purposes only. It is designed to provide general information about different technologies, their applications, and their operational principles. We are not affiliated with or representing any specific equipment manufacturer, distributor, or product line. The inclusion of any specific products or features is solely to illustrate concepts and should not be interpreted as an endorsement or promotion. Attendees are encouraged to conduct their own research and consult with SMI when selecting equipment to meet their specific needs. So yeah, just don't want to give anybody the wrong idea. If you see a lot of photos of one particular type of equipment, that is just a coincidence. Learning objectives today. First, we're going to understand boiler blowdown basics. I think blowdown as a concept may not be familiar to everybody. Then we're going to understand heat recovery as an energy conservation measure. We're going to understand key design and operational considerations for implementation of a blowdown heat recovery system. And we're going to understand energy and water savings calculations associated with the opportunity. As an outline, we're going to go through the boiler blowdown basics. We're going to talk about what is blowdown heat recovery, which I'm going to abbreviate as BDHR for a lot of the presentation. When does blowdown heat recovery make sense? What are the design and operational considerations? We'll go through an example opportunity, and then at the end we'll have some Q&A. So the first section, boiler blowdown basics. Here's a typical steam system. You have your boilers here. Let me get my laser pointer here. Boilers here, your steam's going out. You have some amount of condensate coming back in, so as much condensate as you can get back, but there's always system losses. And then whatever is lost is made up through makeup water. In this system, we have a surge tank where condensate and makeup water are blended. They go to the deaerator. That is heated to deaerate the water. So there's a steam consumption here. And then the deaerator will feed. From here, you're going to call this feed water typically, and you're going to feed the boilers with that, and they're going to generate steam again. What we're concerned with is this other stream here, which is the blowdown, and that is a stream coming off of the boilers to remove impurities, and we'll talk more about that as we go. This is the blowdown necessity cycle that I've made up. So we have makeup water adds dissolved solids to the system, typically abbreviated as TDS, total dissolved solids. Steam leaves the boiler as pure vapor, and TDS accumulates in the boiler. So as the boiler generates steam, all the steam leaves those impurities behind, and they start to concentrate in the boiler. Blowdown removes that TDS. So it is a stream of water rejected from the boiler to carry with it the total dissolved solids. As the system losses drive additional makeup water, more makeup water is introduced, and it continues to add dissolved solids, and the cycle continues. Why is it necessary to remove dissolved solids or solids in general? If not controlled, high dissolved solids can lead to scale formation. which can reduce heat transfer efficiency, lead to hot spots, premature tube failures. Basically, scale is going to insulate your boiler tubes, and even a 1/16 of an inch of scale can reduce or can increase your tube wall temperatures by hundreds of degrees. So it's making a big difference in the lifespan of your boiler tubes, and as well as your thermal efficiency. What it's also going to do is it's going to cause foaming. So as the dissolved solids build up in the boiler water and steam is generated, it will start building up a kind of a foam or like a scum layer on the top of the boiler water. If that foam gets significant enough, it'll start getting carried away with the steam. So then you're getting this dirty foam in your steam, kind of giving you wet steam and dirty steam. You will notice spots on, say you were cleaning medical equipment in an autoclave. You'll start noticing spots on the equipment, just getting poor results. But also just getting wet steam and fouling in your steam system. So it leads to a lot of problems there. Another thing it can do is foul up your level control equipment, which can lead to a dangerous scenario. That's one of the most important safety devices in the boiler. The scale can build up in there, but also the foam in the water can lead to kind of false readings in your level controls. So it is absolutely necessary, but it is inherently wasteful. There's two main types of blowdown, surface blowdown or continuous blowdown. These are the same type, so this is just one type. They're called both. This is located at or near the normal water line. Most of the dissolved solids in the boiler are, from about 6 to 8 inches from the top of the water line. And so you'll locate the surface blowdown line in that area. And it's basically based on the circulation pattern of the boiler where it's located. You want to put that position in a location to ensure the most concentrated water is rejected, and you want to avoid, rejecting incoming feed water or chemical feed. So this is a strategically located blow continuous or at least frequent. And a 2 to 5% of steam flow is typical for a well-maintained system with good condensate return. It's commonly controlled by TDS, which is typically measured with conductivity. So you're talking about a lot of metals left in the water, and the more metals there are, the more conductive the water is. So it's actually measured with conductivity. The control configurations here, you can have different controls. More crude controls are going to give you more blowdown flow. So just upgrading those controls can represent an energy conservation measure as well. But it also may represent a large amount of blowdown flow that you can capture. There's manual controls like intermittent or continuous. Continuous would be like something like this with a valve with a position indicator on it that's adjusted from time to time by the boiler operators to try to ride a certain TDS level in the boiler. And then intermittent would be a valve that they come out and actually just blow it down, similar to the way they do bottom blowdown. Automatically controlled this blowdown, that's what you're going to see most of the time nowadays, especially on newer systems. That's going to look something like this, where you have an actuated valve, whether that's an on-off valve or a modulating valve. You're going to have a conductivity probe measuring the conductivity, and you're going to have a controller that is actuating the valve. Regardless of the control configuration, the solids accumulating inside the boiler dictate the blowdown amount required. So the calculations that we'll go through later will be a good estimate of blowdown regardless, and then it's just how close are they controlling the blowdown to what is actually needed. The other main type of blowdown is bottom blowdown or intermittent blowdown. I should say that's not what this presentation is about, but I'll go through it real quick. So this is located at the lowest point of the boiler or mud drum in a water tube boiler. It's common to have one at each end, and basically you have two valves here on each end, or maybe a common, but this is your slow opening valve. The procedure is you're gonna open this slow opening valve, and then this is your quick opening valve. You see the big handle there. You can quickly open that, and you're gonna blast water out of the bottom of that boiler to try to remove sludge. So not dissolved solids, but settled solids for the most part. So this is typically performed by an operator. It can be timer based or automated. Most systems, at least most of these systems that I see, are going to be manual. Larger, like utility scale type boilers, maybe are going to be more automated. These are performed infrequently compared to surface blowdown. So like once a shift is typical. So this represents a lot smaller energy waste than surface blowdown. And it is, literally a few minutes every 8 hours. So it is not a good candidate for a heat source for, a heat recovery opportunity. And then this bottom picture here, this is the mud drum of a water tube boiler. So same idea, you have your quick opening and your slow opening. Then I should point out the second valve is your section 1 code limit on most boilers. And that will be important later when we talk about different configurations. Again, this is not what the subject of this presentation as far as a heat recovery opportunity, but it's important to know. The energy wasted here. So what are we talking about? Blowdown is necessary, but it is inherently inefficient. So you're heating up feed water to saturation pressure at the boiler. If you're at a 100-pound boiler, I believe it's like 340 degrees or so. So you're heating water up all the way to that temperature, and then you're just rejecting it and blowing it down the drain. So there's a significant amount of thermal energy there. You're talking about 2 to 5% in a well-maintained boiler, 2 to 5% of your total steam flow. That's a significant amount of energy. And when it's discharged without recovery, all of that energy is lost. And there's some more losses as well, which we'll go through. What is lost? So you have your sensible heat, obviously just heat in the blowdown that you could capture. When that blowdown drops pressure, some of it flashes, say 10, 13%. That is clean steam. So that flashes as clean steam, just like the steam in the boiler leaves the impurities behind. So does that flash steam. So that could be used if you can capture it. And then tempering water. So I want to show this diagram again because in your bottom blowdown tank, typically you're at atmospheric pressure and you're going to be discharging liquid at 212 degrees. While most facilities have a sewer limit of 140 degrees is typical. And so you will commonly see like a tempering valve on these bottom blowdown tanks. And you're basically just spending city water to cool that off just to get it below temperature or sewer temperature limits. So you don't damage your your drainage system. So that is a significant amount of waste. Also, you're also losing some treated boiler water chemicals and some mechanical energy just from what you're spending to generate steam or generate saturated water in the boiler in this case. And so there's a lot of loss here, but I would say the three main components are those first three in bold, which we'll talk more about. All right, next section. What is blowdown heat recovery? We've kind of talked about it a little bit, but basically captures that waste heat before it's discharged, transfers the energy to a useful heat sink, and provides overall boiler plant efficiency improvement. It should be noted this is a non-interfering system. So this operates downstream and independently of your boiler blowdown controls. It doesn't require a change in blowdown rate or chemistry, although some systems would perform better from a digitally controlled blowdown or more steady flow. But generally speaking, it doesn't change how your boiler is operating. And it could be completely bypassed and isolated, and you could continue to operate as you've always been operating. So it's kind of a passive, not passive, but a non-interfering system that can capture a lot of energy and save a lot of money. Here's the system again, just as a refresher. So again, we're going straight to the bottom blowdown tank. What is different with a blowdown heat recovery system is you're going to look like this. So your blowdown, again, this is surface blowdown, not bottom blowdown. Bottom blowdown is not really shown here. It's just not relevant for a heat and mass balance. So surface blowdown is going to go into your flash economizer. That's this on this example unit here. That's this inlet. So you're going into your flash tank. Some of that steam is flashing off. You're going to use that in your deaerator. The drain is going to settle down here, or the liquid is going to settle down here. That's going to be a heat sink for this makeup water coil that you can see. The makeup water is going to come in, be preheated, and leave. That's shown here. And then the drain is going to continue on to your bottom blowdown tank, but it is going to be significantly cooler than it would have been otherwise. So what is saved here? So first you have your flash steam, right? We just talked about. That's clean steam that's being captured. You're sending that straight into your deaerator, downstream of your PRV, and then your PRV is making up the remaining demand of the deaerator for steam. This is like a balanced line. So your flash economizer, your flash tank is going to basically operate in balance with your deaerator pressure. And that pressure is going to drive how much flash steam is available from your blowdown. So your boiler operating pressure, you're reducing down to that flash tank operating pressure. That determines how much flash steam comes out. Next, you're going to have your makeup water is going to the unit and it's recovering heat. So the liquid is, you're getting some heat recovered out of that liquid. And then your last savings component, which is not insignificant, can often be, 30% of your savings, but is this tempering water that's saved from not having to temper that blowdown drain. It's reasonable for a blowdown heat recovery drain to come out at 100, 110 degrees. So you're well below your sewer limit, or you can be, and you pretty much eliminate the total requirement for tempering water, at least for surface blowdown. Some common configurations. So these are just different examples of unit designs. There's different manufacturers of each. These are just examples, but I will say Pin Separator was kind enough to give me some information, as well as Alstrom. So I appreciate that. But this first example is a pin separator unit that's a flash tank with an internal heat exchanger, like what we just looked at. Basically, your makeup water here is in this coil. We just talked about that. And basically, the heat exchanger is submerged within the tank. So that allows heat from the hot blowdown liquid to be captured. This is typically used for makeup water. Because the heat exchanger is immersed in the tank, the surrounding liquid volume acts as sort of a thermal buffer, or like a thermal flywheel. So that smooths out heat transfer during intermittent blowdown events. So if you're kind of controlled on intermittent blowdown, it provides a little bit of a buffer there. Next is kind of the same idea, but with a separate heat exchanger. So if you put this in your PFD, or in your heat and mass balance, it's going to look kind of the same. You have your blowdown coming in, flash steam coming out. You have the drain going to a separate heat exchanger, heating makeup water. I'm really kind of showing makeup water in all of my examples here, but there is other opportunities for heat recovery as well, which we'll talk about in a minute. But the most common is makeup water. The advantage here is that it allows the flash tank and the heat exchanger to be designed and maintain as separate components, so it can offer flexibility in the equipment design and selection, as well as maintenance. It could be easier to access. That's another example. And then this last one is by, this image is provided by Alstrom, but this is one of their self-contained heat recovery units. This is an interesting design. It's kind of uses the flash steam within the unit. So the blowdown comes in, it flashes off in this flash tank. The drain goes into one tube bundle and heats the makeup water, and the steam goes into a second tube bundle to further heat the makeup water. What's interesting about this is, again, the steam flashes off clean. Once it condenses back down, it is clean, basically treated boiler water. And so it discharges into this makeup water line. So you're also getting that water savings from this unit. So I think it's an interesting configuration. And then the last one I'll mention, and this is not an exhaustive list, but these are just like some common ones that I've seen. But this is a high pressure side heat exchanger. And the difference here is that you are putting your heat exchanger upstream of this blowdown valve. So before you drop pressure and let your blowdown flash, you're putting it through a heat exchanger and just going, liquid to liquid on your heat exchanger. The advantage here is that the blowdown is hotter, so you have a larger temperature to work with. The disadvantage here is a little bit more complicated because you might be within your boiler code limits. And so the materials of construction would be more stringent. But yeah, it's another option. What are the potential heat sinks? So system makeup water, I've mentioned multiple times, that is the most common. You could also use the blowdown to heat boiler feed water. I've seen systems where they use it to heat like their fuel oil. Fuel oil has to be kept warm in order to handle it and use it in the burners. It's getting a little bit scarcer to see boilers using number 6, but they still exist. And any other processes. So this is a source of heat, and if you can find an applicable use for the heat, you can do that. As well as the flash steam. If you have a low pressure steam system in the area, you can flash steam off and use it in that system. It doesn't have to be used in the deaerator. It just so happens that the deaerator is typically going to require more steam than you have available in the blowdown system, and so it is a good constant user of the steam and a good application. When does blowdown heat recovery make the most sense? So this is like, if I go in a facility, what am I looking for if I'm going to start thinking about this? Generally speaking, it's going to work better with moderate to high boiler pressure. I would say greater than 50 pounds. I do want to stress that these are general clues, not hard and fast rules. But the higher the pressure, the more energy that blowdown has. Obviously, higher annual operating hours, higher fuel cost, higher steam loads, kind of like any other energy conservation measure, right? Like the more it's used, the more energy is available to save. And that's true here too. Specific to blowdown heat recovery, I would say a high surface blowdown rate, which is going to be driven by poor water quality or poor water treatment, poor condensate return, as we'll see in our example in a minute. All of your dissolved solid, or most of your dissolved solids, are being introduced through your makeup water. If you require a lot of makeup water due to a poor condensate return rate, that can really drive up the dissolved solids in your boiler that have to be removed. So that can drive up your blowdown rate. You want to have a reliable heat sink. If they're using an atmospheric feed water tank, there's nowhere to grab the steam. Maybe they have an irregular way of controlling their makeup. It might just be too complicated. But if it's kind of a standard boiler plant, a lot of times you're going to be able to put that heat somewhere. If you have poor boiler combustion efficiency, that's actually good for this, as a lot of energy conservation measures. The less efficient the boiler is, the more fuel per amount of steam is saved. So if that makes sense. So system efficiency is not as important because we're conserving all of our energy here within the boiler plant. So it doesn't really affect steam out and condensate back as much. We're offsetting this steam flow right here. Blowdown heat recovery generally is going to be most effective where surface blowdown rates are high and a consistent heat sink exists. Some indicators of marginal or poor candidates: if you have lower pressure boilers, any Section 4 boilers, these are pretty rare to see. But generally, even under 50 pounds, they're going to start falling off. Limited run hours, low steam flow. I would say maybe 20,000 pounds per hour or up is, I'm really leaning towards looking at this. A high condensate or low makeup water, or if they have optimized water treatment, so like a softener plus an RO skid. And obviously, good water treatment is not a problem. It just means there's going to be less dissolved solids, which means less blowdown, less recoverable energy, and it's going to make the economics more marginal. Again, these are not hard and fast rules, because you may see an RO skid because that particular system, the users consume a lot of the steam, and so there's a very poor condensate return, or they just have a poor condensate return system, or a deteriorated condensate return system. So an RO skid doesn't necessarily mean that it doesn't work, but it's just a clue. Some key design considerations. So okay, you have to bear with me here. We're going to start getting into the weeds in a minute, but some things to think about I'm saying process design, but also like assessing the opportunity. So what is the steam load of the system? What are the operating hours, operating pressure, the aerator operating pressure, combustion efficiency of the boiler? What are your utility costs, fuel costs, water costs, chemical treatment costs? And then you're going to want to get your hands on water treatment logs, makeup water analysis, things to do with the quality of the water, so you can get some clues as to how they're operating their blowdown. But overall, I would say the number one piece of information you want to know, in addition to just general steam demand, is your blowdown percentage. And the clues here are going to be your makeup water analysis. Even better than that, I would say, are the boiler water treatment logs, because you might just straight up have conductivity or TDS readings on those. Conductivity controller settings, and makeup water and or condensate flows. So if you look at the equation here, this is solid in your feed water. Again, your feed water is the water coming from the deaerator to the boiler. So it's a mix of your makeup water and your condensate return. So in order to calculate this is what you need to calculate blowdown percentage. You need some combination of these variables, which are makeup water flow, makeup water TDS levels, condensate flow, condensate TDS levels, or you might possibly have your TDS levels in your feed water in your water treatment log. So it depends where they're taking samples at. It depends what information you have. Sometimes you just have a rough idea of condensate return and maybe a makeup water analysis from the water utility, and you can get to a reasonable TDS level in your feed water. In the end, once you have that, you can use that and what the boiler recommended limit is, or you can use what they're controlling to. You can find on the controller screen, and you can calculate the blowdown percentage. So that's your waste heat stream that's going to drive the energy savings for the whole deal. Here's an example of a water treatment log. So here you have the boiler feed water conductivity. So boom, you have it right there. If you know the level that they're controlling to in the boiler, you can calculate blowdown percentage. Maybe you don't have that though. Maybe they're just showing you conductivity, and the outlet of your softener is your makeup water. You can see that it's much higher. So you're seeing readings in the 400s here as compared to in the teens here. So this particular facility has a good condensate return, and so the boiler feed water is a lot closer to the condensate conductivity than it is to the makeup water conductivity. But that can easily change, with your change, like with a change in condensate return percentage. One thing to be aware of is that there is an impact on surface blowdown with chemical treatment. There are certain chemicals that are designed to bind or react with dissolved solids, and kind of, they say they sink them to the bottom, and then they're being handled by bottom blowdown. But in reality, though, most of the chemicals their goal is to make the dissolved solids less adherent. So they're more focused on reducing scale than sinking dissolved solids. And if someone's claiming that they reduce blowdown by 50% with using a certain chemical, it's probably paired with some other improvement in their blowdown procedure. Generally, it's going to reduce your blowdown, less than 20%. I would say just your chemicals, because most of them are still going to be removed through your surface blowdown. The chemicals are going to help with scaling more than, I would say, sinking dissolved solids to be handled out of bottom blowdown. That being said, chemical treatment is very important, and as we mentioned before, scaling is very bad in a boiler. So we want to make sure we do have a good chemical treatment program. The point here is that it may not significantly change your blowdown requirements. Some other things to think about: how is blowdown controlled? Is it intermittent or continuous flow? That might affect your selection of your blowdown heat recovery equipment as to, how it can handle, loads or flows that aren't continuous necessarily. Here's another example of a good kind of typical control, surface blowdown control system that you would see. This is your connectivity probe. You see these often looks just like this. It's sitting down the surface blowdown water. And then you have this controller here modulating an actuated ball valve just like this. And they often look exactly like this, but across different manufacturers may have a different color actuator. The ball valves are usually this type of ball valve, and this is a pretty typical looking setup. So if you walk in a commercial boiler room in America and you trying to find the surface blowdown control station, it's going to look something like this most of the time. Some other concerns: materials of construction. Again, we're talking about code compliance. So if you're in a boiler room with a boiler with decent pressure, you're probably designing to be 31.1. You are connecting this system from the boiler, the blowdown line from the boiler to the bottom blowdown tank. You have a steam connection to the deaerator, and then you have makeup water connections. So you have a variety of materials and pipe sizes that you have to run, and you need to worry about your minimum and maximum flow. So when you're thinking about it as an energy conservation measure, you're really kind of smoothing that flow out, but you do need to consider what the maximum flow will be to the tank and how much it can handle. The pipe routing is always kind of part of the equation. Sometimes boiler room layouts are different. As I mentioned, you have to connect to all those different pieces of equipment, so you have to run pipe to all of them and what's the best location to put the thing in to minimize costs. These projects are, I would say, most of the cost is in the piping installation and not in the unit itself. So that's always an interesting part of the puzzle. And then M&V, how are you going to measure the performance of the system? I would say that we often see this as a sub-measure of like an overall steam plant optimization measure, where they're using like option C to evaluate, boiler plant fuel consumption before and after implementation. And they're pairing this with maybe other boiler plant upgrades like an O2 trim system on a burner, or maybe a new boiler altogether, or optimizing a deaerator, or steam plant or boiler plant pressure reduction optimization, or whatever the different measures are, and they bundle them together as an overall steam plant optimization measure. Some other design considerations like maintenance and operability. I would say heat exchanger cleaning. So if you think about, this is dirty blowdown water being used in your heat exchanger, it is going to eventually need to be cleaned, and you need access for that. So that's always something to think about on these. Okay, so on to an opportunity example. This is a VA hospital operating central steam plant boilers at 100 pounds. The system has experienced very poor condensate return, which drives high makeup water demand. The boiler plant utilizes water softeners for makeup water treatment. Surface blowdown is currently controlled on conductivity. So this particular plant has a deteriorated condensate return system. They have given up on returning condensate from a lot of the users in the facility, and they're basically dumping condensate to ground. So they have only about 20% condensate return. Some inputs here. Operating pressure 100 pounds, steam flow 11,500 pounds per hour. So that's something to note. This is a pretty modest steam flow. But again, condensate return only 20%. Your makeup water, this is a pretty reasonable level on your TDS. This unit is micromose per centimeter. You also see like micro Siemens. There's different units for these, but they can all kind of be plugged into the equations that we're going to use as long as you keep your units consistent, because they do cancel out. This is a typical boiler limit for a fire tube boiler, 3,500 micromose. That equates to around 2,100 parts per million of total dissolved solids. You got a water and sewer cost. This is kind of a reasonable number. This is kind of a typical chemical treatment cost, 0.4 cents per gallon. This is a pretty modest fuel cost, $6.4 per million BTU. In the Northeast, you're going to frequently see over $10 per million BTU on that. Combustion efficiency pretty low. The boilers have had some scaling issues. And an operating pressure on the DA of 5 pounds. So that's a lot of numbers here, but it will get interesting. Let's see what we have a question here before I get into it. Due to the added system complexity from the BD equipment, wouldn't it make sense to invest in a better water filtration upfront and possibly eliminate the need for blowdown? Or is it unrealistic either due to the scientific constraints or economic constraints? That is a good question. I would say that yes, improving your blowdown situation is also an energy conservation opportunity. So water treatment systems can be expensive. I would say they're probably going to be more expensive to implement than this. And then you're still going to have some blowdown. So this is going to capture a lot of the energy in the blowdown, whereas another like an improved water treatment, right? You might drop your blowdown from 4% to 2% or something. Whereas here, maybe you're capturing 80 to 90% of the energy, right? So and also eliminating the tempering water. So I don't know. That's something to evaluate for sure. And good water treatment is good. You can also reduce your blowdown by improving your blowdown control. So upgrading blowdown control. And sometimes these units will be packaged together with an improved blowdown control, and that helps smooth out the blowdown flow to the unit and promotes, better heat capture. Okay, so step one here, we're going to calculate the blended feed water TDS. So in this example, we're lucky enough to have those conductivity readings. We have a fraction of makeup water 80% times the 500 micromose reading times plus 20% times the 50 condensate return reading. And we're getting a feed water TDS level of 410 micromose. That's pretty high, I would say. As you can imagine, if this number was 80% and this number was 20%, then this blended TDS level is going to be a lot lower, right? So that's a pretty high feed water TDS level. Then from there, we're going to calculate the blowdown rate. So we have our TDS of our feed water. We have a conservative boiler TDS level of 3,500 micromose. That's kind of typical for a fire tube boiler. Note that this top equation, like I mentioned, it works with all different units of conductivity. because the units cancel out. So it's a ratio, right? So if you have everything in microsiemens or parts per million, whatever, that equation still works. But in the end, we come up with a blowdown percentage of 13.3%. Remember, I mentioned that typical is 2 to 5%. So 13.3% is pretty high. I think the highest I've ever seen is 19% at a chemical plant once. But this is a high blowdown flow. So even though we have a low steam flow, we're blowing out 13.3% of our boiler feed water. We're blowing down the drain. So we can convert that to a blowdown flow, essentially is what we're doing here. So you're taking the steam flow. That percentage is percentage of feed water. So you kind of have to flip the percentage from, feed water and use your steam flow. So in the end, this is your feed water flow that you're determining based on that blowdown percentage. You can use that in your condensate and makeup water percentages to determine those. But in the end, what we're concerned about is this blowdown flow. So this is your energy stream, 1,759 pounds per hour of saturated liquid at 100 pounds. And that's a pretty significant energy stream, relatively speaking. The rest of the calculation is going to be done. I could go through all of this, but really the best way to do it is to plug in this economizer into your heat and mass balance. And you can see the whole system operating before the blowdown heat recovery and the whole system operating afterwards. And all of these calculations are basic, thermodynamics, heat transfer, whatever you want to call it. But it's basically, heat and mass balance formulas of conservation of energy and mass. So that's how you would come up with the rest of the savings. Once you have that blowdown flow, you're calculating how much flash steam is flashing off, how much heat transfer is going to the makeup water, how much steam that's offsetting downstream. And so it really is just a heat and mass balance type of calculation. The results from this particular example, you're going to take that blowdown, you're going to route it to a 5-pound flash tank, recover that low pressure flash steam, like we've been saying. Remaining liquid blowdown passes through a heat exchanger to preheat makeup water. The makeup water temperature is going to increase from 60 degrees to 79 degrees. So that's the impact there. So instead of making up 60-degree water into your system and cooling off all that condensate, you're now making up with this significantly higher temperature of 80 degrees. It still requires steam to get it up to that saturation temperature at 5 pounds in the deaerator, but requires less steam, right? Your blowdown discharge temperature is reduced to 110 degrees, eliminating the need for tempering water, and both flash steam and liquid heat are largely recovered and reused in the plant. Annual savings here is 3,000 million BTUs per year. Your fuel savings is basically that divided by your boiler combustion efficiency. You're getting 4,365 million BTUs per year. Significant amount of water, but the punchline here is this is almost $57,000 per year in savings and 255 tons of carbon per year. That's a significant amount of savings. The fuel savings alone represent 2.6% of the annual fuel costs of the system. I would say what is typical for a blowdown heat recovery system, probably about 1 to 5% of total boiler fuel. As we have seen, it is dependent on a variety of variables. So this is, always kind of, there's clues, but you always kind of got to run the numbers to make sure it works. How does this fit into an ESPC? I really like this, and I think this maybe is the most important takeaway for a lot of our viewers, especially our viewers that are in the ESCO world. But we have an installed cost. That's my estimate at your installed cost to your customer, not our cost to you. But I'm saying installed cost of $300,000, a potential rebate of $1 per therm. I think this is conservative. If a rebate exists, $1 per therm is pretty conservative. So that's $37,900. So you have a net financed amount of $262,100. Annual savings again, $56,833. 15-year financing at 4%. You have an annual debt service of $23,600. So you have a net positive cash flow on this opportunity of $30,233 per year. This is a contract driving measure when the variables are conducive. This is a simple payback after the rebate of 4.6 years and a savings to investment ratio of 2.4. Just as a reminder, anyone like this is evaluating projects, anything over 1 is good, right? Like, so 1 is basically no benefit. 2.4 is great. So this is a really good measure in a lot of facilities and really could fit well into a performance contract, especially if you're already looking at optimizing the steam plant anyway. This is kind of a no-brainer. Some lessons learned: controls often limit recovery. System changes can dramatically affect potential. So a significant improvement in condensate return could potentially significantly reduce your blowdown and thus your energy source. And then also maintenance drives long-term performance. So these things do have to be maintained. Sometimes it can be years between cleanings. I've seen recommendations that you clean after the first year, maybe clean after the second year. If it's not that dirty, maybe you can extend that out, but you do have to plan for some maintenance. But it's a significant energy source. And this photo here, when I think about lessons learned, this is a capped surface blowdown line, so that is not a good idea. Doesn't necessarily have to do with these bullet points, but definitely I'm sure they're learning a lesson on that. Key takeaways. Oh, I got a question here. Let's see. Where in the US are these projects suitable to have rebates? How are they evaluated? Parameters, savings, flows, etc. That is a good question. And different utilities have different approaches. If they have custom thermal rebates or custom gas project rebates, the calculations for this measure, they're tried and true engineering calculations. There's no pulling the wool over anybody's eyes or anything like that. It's very straightforward. You can give it to them with a very defendable methodology. And in my experience, you're going to apply for a custom, gas savings or thermal heat recovery type of rebate application. So yeah, somebody commented Illinois People's Gas pay $1.50 per therm on first year savings. So maybe that rebate is just the 1 year. I think that's probably typical. I know National Grid in the Northeast, they have $2 per therm on stuff like this. NYSERDA has rebates for stuff like this, and other utilities as well. So there are certainly utilities that don't have any rebate available. If you take the rebate out of this equation, it still is a contract driving measure in this example. So I guess that's the takeaway to me. And it doesn't always work, but it definitely can work. And if you use the clues that I've given you, or just let us do it, we can evaluate that for you, and we'll leverage those savings to do other things, right? So that's the takeaway. Okay, so here are the key takeaways. Blowdown is a significant energy loss. Heat recovery is proven and reliable. Engineering assessment determines viability. So as we've gone through this, I mean, you see there is some engineering required here. It's not well, I got a 700 horsepower boiler, so I'm going to put this size blowdown heat recovery, and I'm going to generally get this. It's not a table lookup. It's although it can be, but you're not going to get detailed results or expected results from that. So it does require some engineering, but that engineering is based on standard engineering principles. This is a proven technology, and these are generally pretty robust systems that can be pretty reliable. So I guess those are the takeaways. I got another question here. Most of the blowdown systems in Kenya are manual with a lot of intermittency on off, say every 8 hours. Does this still make sense to recover? Um, that is a great question, and that's funny that you say that. Actually, this P&ID right here is from a project where they had manual blowdown, and this was a two-part project. And this is so we recommended a digitally controlled modulating blowdown valve. And so that was one aspect of the savings was they are now controlling to they would now be controlling to a conductivity reading and modulating that flow and minimizing the amount of blowdown lost. So they're just rejecting exactly the amount that they need to keep the TDS levels appropriate. So that's part of the savings. And then they still do have a blowdown requirement, and it was still enough to warrant a blowdown heat recovery system. So that's where I pulled this from one of our projects. I would say I would evaluate that. Again, if it is, a small flow, like if you're talking about 10,000 pounds per hour with a good condensate return, it may not have a decent enough payback, but otherwise, large flow, decent pressure, kind of standard water treatment, it starts becoming a real opportunity. So hopefully that answers your question. But you could pair, I guess the long answer short, you can pair the blowdown heat recovery with improved blowdown controls as well. So yeah, that's my recommendation there. And that is the end of the presentation. So I will stick around for any additional questions. We are going to have another webinar on March 10th, which you can register for at the link that Ashley just posted in the chat, or you can scan the QR code here. We hope to see you there. That's going to be a showcase webinar. We have a guest speaker, and we'll be sending out more information on that shortly. This webinar and past webinars are available on our website, steammgt.com/webinars. I also, we like to get out and do presentations for teams in person or even just virtual presentations for, a focused group. So if you have an interest in a STEAM presentation for your team, please reach out with this QR code, or you can email me directly. This is my email here. Again, the PDH certificate, if you do want that for, PE or like PE continuing education or a CEM or whatever your technical certification is, we can give you a PDH certificate. You just email me at my email address right there, and we'll get that over to you. Otherwise, I will hang on for a few minutes, see if there's any more questions. I hope you guys found this interesting. Apologies if it got a little in the weeds on the calculations, but I enjoy that stuff, and hopefully you can revisit that, and it'll be good information for you in the future. But yeah, we thank you all for joining us, and we hope to see you next time. And let me know if you have any questions.